Hi, so my name is Clément. I'm a data scientist at Lyft, which is a ride-sharing company that operates in San Francisco and in 60 cities in the US. And so we're based in San Francisco. And today I'm going to talk to you about how we use Python to do data science and why it's important for all the problems we face at Lyft. So first, a little bit about me. So I graduated from Supero and other grand école from Toulouse, and then I interned at Lyft in the summer 2013, when it was like still a bootstrap startup with about 50, 60 employees. And then I went back to school to do a master's at Imperial, and came back to Lyft, and now Lyft has grown to a bigger company, about 400 employees. So my interests are a lot about data science. I like working on problems where we have a lot of data, and that's the case at Lyft. One of my interests is in also in deep learning, and I like to do a lot of robotics also. So what is Lyft? So Lyft is, so as I was saying, a ride-sharing company, and basically, so we're doing ride-sharing at the scale of a city. So if you want to go somewhere and you just like use your app, you tap two buttons, and then someone pick you up, and then you can go to your destination. So what happens is also that anybody can be a driver. So our goal is to have every seat in every car full, so that like we can really optimize traffic. We heard this morning problems with the public transportation in London. Believe me, in the US it's way more complicated. If you take Los Angeles for instance, you have no public transportation. You have no metro. So you have no subway. So the roads are really congested, and it's a really big part of the city. You can have like 6 lanes on the road, and during rush hours it's really bad. And most of the cars on these roads during rush hours are with only one people driving. So our goal is to fill every seat possible, so that it becomes a really efficient way of traveling and solves different issues. So we started into 2012, and now we're about in 60 cities only in the US. We have planned to. We're not international yet, but we will be someday. And one of the icon of our app is the pink mustache. So you might have seen pink mustache in the news, and so that's Lyft. So what do we do in data science at Lyft? We have a lot of really complex problems to solve, and these problems are core of Lyft service. Like, solving these problems is the way we're going to be able to reach our goals, to have every seat full in every car. So among the problems we work on, we work on dynamic pricing to have pricing that change depending on your locations, because it makes sense to have people pay more or pay less depending on if it's efficient for the system. We also work a lot on dispatching. How do you dispatch drivers efficiently to passengers, and what is the best way to do so? We have a product called Lyft Line, which is so the first way Lyft started was what we call a classic lift is just you and your friend maybe order a car and someone picks you up and you go to your destination. But of course, what we want is to be more efficient than that. We want to match people that are going in the same direction, because this is the way we're gonna solve the car problem. So Lyft Line is our real ride-sharing product, which is if you have two people that are requesting from the same area, going basically in the same direction, we match them together, and then it's way more efficient. It's a way of you can divide the cost of the ride. You can make it so cheap if it becomes efficient that it's something that you can compare to the price of your fare if you were using public transportation, compared to the price of a taxi 10 years ago, which is not really not efficient. You can have a way bigger audience and a way bigger market by targeting more, by paying less. So how do you match passengers? It's a real you don't want to match passengers that are like too far away, otherwise they won't like having to do a big detour to go to your destination. They won't like the product, but at the same time you want to match some people, so you can't be too restrictive, otherwise it's not efficient. So this is part of the problem we're working on. Also, having accurate ETAs, so how do you predict the time it takes for you to go to your destination? How much time the driver, when will the driver arrive? And this is also something that the passengers want. Also, we're a marketplace, meaning that we have drivers, we have passengers. Sometimes the demand is really high. Let's say it's 2 a.m. Everybody is leaving the bar, and like at the same time requesting drivers, but maybe drivers don't like to drive at those hours. So how do we make sure that we tell drivers that they should drive at these hours, but and that maybe not during the day at 2 p.m. on a Tuesday where no one is requesting. So how do we match demand with supply? Also, another problem that I worked on, one of the first problems that I started working on actually, is how do we do events detection? So I was saying that we need to match demand and supply. Of course, it's not the same to match demand and supply on New Year's Eve than on a regular Saturday night. So if you have a big event coming on, how do you detect it? How do you how can you incentivize a driver before it happens? So this is really a really interesting problem to work on, and one of the cool things that we have is that we have so much data that we're capable of detecting just by itself events. And so when I moved there, I was obviously French. I didn't know much about what was happening in San Francisco, and so working on this was actually really interesting, because I was like, okay, something weird happened on the 6th of August. So what happened? And it's outside Lens, like a big music festival in San Francisco. And so just by looking at our ride volume, we can do cool things like detecting big events like this, or detecting when the Super Bowl starts or when it ends, and so it's a really interesting problem to work on. Another big problem we're facing is fraud. So basically, what happens is that we pay drivers. Of course, we take a cut from the price we ask to passengers. But if let's say we take a certain percentage, if there is fraud, so if someone requests a ride and like at the end of the ride doesn't pay, we still have to pay the driver. So and then we'll pay him like the full price. So if we have like even a really small percentage of fraud, means have a really big impact. So let's say we have like 5% fraudulent rides, and we take 10%, then it's half of our take that goes into fraud. So it's a really big problem that we're working on, and that is also really interesting. How do we find fraudulent passengers? How do we anticipate before we have to pay? And a lot of these problems have a component that you face in a lot of startups and in a lot of companies. What makes it even more challenging for us is the fact that a lot of them are related to geolocation, and this brings more like this makes the problems more challenging and more interesting. So we can dive a little more into some of those problems. So the first one is dynamic pricing. So we have, let's say we want to cover a whole city. Of course, there is part of the city that are neighborhoods with a lot of activity. So let's say you're out at night at 2 a.m. and it's so you're in a bar area where a lot of people are requesting. The goal is to have the prices change so that we can, in the end, lower the price. So it's not about having like making people pay more when we want because there is more demand, so we can make more money. It's about being able to deliver the lowest price in the end. So if you basically what happens is that if you lack drivers somewhere, you want the drivers to be able to go drive there. So it's a way of making sure that we have drivers in the right place, because we show them a heat map like this on their app, so they're capable of learning and knowing where there is demand at what time, which is really important in terms of efficiency. So if you think about if all the drivers are not where the pickups are, then you have to pay them for, like, Lyft has to have way more drivers, because the time they're driving toward the pickup is useless for Lyft as a system, and it's something we really want to minimize. Is the ETAs the passenger sees. So, and the bigger we grow, the denser the market becomes, then the smaller these ETAs become. And if you have small ETAs, then it means that drivers have passengers in their car almost all the time, and then it means that you can guarantee them the same amount of money on 1 hour and make the price lower. So it's a win for everyone having this kind of system really well developed. So yeah, so it will automatically increase in some areas, but it's a complex problem. Like how do you where should you price? Should you say it's only, like, let's say you're in the suburbs, for instance, and of course there is not many car driving around because, well, there is not many requests. So should you price more there, or should you? But at the same time, it's a really low area, and it's already the driver will take time to pick you up. So it's a bad experience for the passenger, because it will take time for him to go there, and so should we make the price even higher? So these are problems that we're trying to tackle, and of course for each of these problems we have metrics that we check and to make sure that we are actually doing good and going in the right direction on these problems. Another one is like how do you dispatch drivers? So let's say we're in a really undersupply scenario where you have only 2 drivers to cover this whole area in San Francisco. So if this happens and you have a request that is really far away, well, dispatching these drivers to this request will mean that for like 16 minutes or so, the driver won't be able to do anything for the system. So this driver is lost for 16 minutes, but you're really undersupplied. And maybe in 1 minute you'll have a request really close to the driver. So how do you decide which request should we match to the drivers, and which driver should you match to the passenger? It's the same in the opposite way. It's exactly the same. Like you have one request, maybe you'll have a driver dropping off someone really close to the request. So maybe the person won't be able to request now, but like in 30 seconds he will be, and it will be way more efficient for Lyft. So yeah, in the end also a really hard problem. It's a really interesting problem to work on, and we have basically two variables that we want to minimize: so the pickup time and also the idle time of the driver. So if you say, I don't want to pick up anyone that is less than 1 kilometer away. But if we do this, then maybe the driver will wait too long, and because he won't pick up anyone. So it's a trade-off between trying to minimize the pickup time and the idle time of the driver, so that we stay really efficient, and also that we guarantee good service for everyone. So I was talking about line matching. How do we choose who to match? So we have a different and it's a complex problem, because it's often the case where optimizing for the system is not the same as optimizing for a person. So if you let's say you're a person, and the algorithm says that the more efficient way is to match you with someone, and in the end you feel like you're going the wrong direction when you start. So, and even if the two persons are really close, and it makes sense from a system to do this, for the first passenger will be pissed because he has to go in the other direction. So trying to so it's also a trade-off to find how do we match passengers so that people are happy, so we can ask them at the end of the ride, do you think that this matching was a good one? And so, yeah, so it's really also a really interesting problem to work on. And also, so what I was saying is that with Lyft Line you can really make the prices go really down a lot. And we're also having features like so if a driver, so yeah, anybody can be a driver. So it's really a really simple process to sign up to be a driver. So yeah, anybody can be a driver, and if you're going to work, you can set your destination as a driver and be guaranteed to have only passengers that are going in the same direction as you, so that we can solve commutes in the morning, for instance. So by doing this, we optimize and we reduce the cost, and also we're always testing new things about this. And one new thing that we're now testing in San Francisco is to have these hotspots where if you set your pickup destination to be there, then it's a really low price. So for instance, in the whole blue area, it's $3 to go everywhere in the city. So if you compare this amount, $3, to the price of a metro ticket, or it's really close by. So if it starts to be $3, then people will think it as a real option for every day, every morning, and every night commute. And so yeah, by doing this, we match people only in one place, so it makes the detour in the pickup time really small. So it's a really nice efficiency that makes it possible to lower the prices. Why do we need also accurate ETAs, and how do we achieve accurate ETAs? Is that so you have to. It's interesting for the passengers to know when the driver is coming, of course. So he can have an estimation of when he's going to be at his meeting. So he doesn't want to be late. So we have to guarantee a certain knowledge about this information. It's also really useful because it's the way we order drivers for dispatch. You want to have the driver that is the closest to you, not in distance, but in time of traffic. Let's say you're on the freeway and it's going. The next stop is really far away out of the freeway. So if you match this person really closely in terms of distance, it's not the best case. So we have to have good ETAs for ordering drivers also. And at last, for Lyft Line, what we do is we guarantee a price before you pay you take the car. So and while we pay drivers the same way taxi do pay the drivers is that it's a function that is linear in terms of time and also distance of the drive. So if we do this, it means that we have to know what will happen during the ride. Like if there is a big traffic, then the driver will have a lot of money, but we will have guaranteed the price. So Lyft is losing money on this. So it's really important for us to be, if we want to continue with this feature, to have good ETAs. And so how do you tackle the ETA problem? And it's quite interesting because it goes what Gael was saying this morning is that sometimes the big data approach can be really simple and provides really good results. So our first attempt to solve ETAs was okay. We have a bunch of locations from the client. We know we want to match those locations to find the route, which route is the driver on, which street is he on, and which direction is he. And then once we have this, we can do, okay, so we have the streets, we know where he's going, we can like use an algorithm like you have on your GPS to find all the roads he's going to take, and then we have estimation from our past data of the speed on these roads, and then we sum them. So it's like it's a reasonable approach to do this, but in the end it's quite complicated. You have to find the road the person is on, and you have to have a good estimation of the speed of the road. And so we had this first model, and then we tried a really simple model, which is you separate the city into chunk of area, and then you just use the speed in between two chunk of areas. So you just use the average speed from one cell to the other, and when you do this, because we have a lot of data on what happens during Lyft rides, because we store user location, so we know a lot about what is happening in terms of speed and traffic. And so when we did this, we had, which is a really simpler approach compared to the first one, but because we have a lot of data, we can it's easier to implement something like this than the first method. And in the end, it's a 30% error decrease in accuracy. So all these problems we have, most of them are solved using Python. We use Python at Lyft. We use Python everywhere. This is really convenient because we use them both on data science to be able to solve this problem, to test new algorithms on these problems, as well as for backend services. So there is such a small gap between working on your project, on your laptop, on your data, and having, because it uses the same language, having it run in production or staging is something that is really useful and helps us implement really fast and try things really fast. So of course we use NumPy, SciPy, Matplotlib, scikit-learn. We rely a lot on pandas also. So I'll explain this more in detail, but we have everything we read from our database can be transformed directly into pandas, and that's how we started working on the problem. We use also a lot of things that are related to geolocation, and so having geohash, that I'll explain this in a bit, what a geohash is. Haversine, which is the distance, it's basically the straight distance between 2 points, except it takes into account the Earth's curvature. And Shapley, which is a package to do geometry. And yeah, so a lot of these problems, because we use geolocation, we rely on both open source libraries and tools we develop. So I have a small demo I can show you. So first, what is a geohash? A geohash is a way to to map to do chunk on Earth, basically having like zones that are described by a string of characters. So if you go really wide, you only have one character, which is like a really big area, and then you can add more characters. And what it does is the more characters you add, the more precise you get. So having like geohash with precision 1 is like huge. It's like the whole Europe. And having geohash 2, geohash 3, and it goes down to like geohash 7 being basically the area of your house, and geohash 8 the size of your bed, to geohash 12, which is like probably this area. So it's a really nice way of aggregating latitude and longitude, and in the end it's a really useful tool. So another thing we use quite often is the GeoJSON format. So what this does is, let's say you want to draw like a shape because you want to run data on some subpart of the region, have like a matrix you want to study. So you can like, and this is like a really useful site if you're doing stuff on this. So you can just like, so on this site you can just draw a polygon, and what a GeoJSON file is, it's a JSON with a certain format for storing geographical data. So in the end you have like all these latitude and longitude for a polygon, for instance. And okay, so once we have this, for instance, let's say we want to study data that appears here in the under the south of the Seine in Paris, south of the Seine in Paris. So I was saying we rely a lot on pandas. We also, at Lyft, we have pandas, and we have a bunch of add-ons that we added to it to be able to get our data faster. I mean, an easier way to get our data to work on. And so let's say we have a GeoJSON that I showed you from this. So from this site you can also store it directly on GIST if you are, or save it as a file directly. So it's really useful. What we can do is, so we load this file, and then so what we want is to fill this file with the geohash that I was showing you, so that we can like have a label to subpart of this region where we can aggregate our data. So if we do this, it will basically create fill this shape with rectangles. So you have a useful function, a useful geohash Python geohash package which does exactly this. It takes the latitude and longitude and the precision, so that I was saying, like 1 to 12. And spits out a string of the number of the precision of the length of the precision, and and so by using Shapely, it's really easy to actually solve this problem of filling this polygon with these rectangles. It has a lot of cool geometry tools that you look. So for instance, if our polygons intersect at all the small rectangles. So once we have this, we also so we can fill this we can fill this list of to this list of geohash. We can affect like a metric. For instance, let's have a random metric between 0 and 1. So for each of those, we have a metric, and we can also look at, instead of just the geohash inside the shape, have all the geohash creates a rectangle. And what so if you take the polygon, you fill all the geohash inside the polygon, and you want also to fill the rectangle the smallest rectangle that contains the first polygon with these geohashes. So what this happens is that in the end, your data looks a bit like an image filled with pixels, and so you can apply filters like. So let's say you want to you have your metrics and you want to smooth your metrics in terms of geography. So you have all these metrics that you read from your data in these small rectangles, and you want to smooth it out spatially. So because it looks like an image, you can use really simple tools like there are on SciPy to apply a filter on it. And what this does what this does in the end, if you speed it out, so we have developed our visualization tool for our data. And so yeah, so what this does is that so on the left you have all right. So on the left you have the first metric, which is the random variables, and so you can look at it, and then after applying the geographic filters that use both the trick of making it an image and using SciPy function, you can smooth it in terms of geography. And yeah, and if we had more data over the week, it's also useful to see how it evolves over time. So this is a tool that we use every day to be able to look at our data and know and being able to see what happens. So as I was saying, everything at Lyft is using Python, and everything is made to make it easier for us to do our job. And one part of this is to have all our data comes into Amazon Redshift, which is a big database or a big data warehouse where every time there is an event happening on the app or that we want to record, everything goes in it, and then we have tables where we separate events that matters to each other and create data that is relevant to each other. And once we have this, pandas is directly linked to this data. So we just by using a simple function we call our SQL query and get our data as a data frame. And this makes it really easy to look at data. So if we combine this tool, the previous tool I was showing you for visualization and this, we have access to our data really fast, and we are able to in 2 minutes be able to answer like small questions about how it's actually going. And at last, we also rely a lot on simulation. So you have a lot of problems you can solve by looking at historic data, but you also have problems. For instance, dispatch. If you change dispatch rules, well, you can't read them from your historical data. So part of our data analysis also rely on simulation. And so yeah, so when it's not historical data, then we do simulation. We replay basically the session's data, and we can tweak a little the parameters. Like what would happen if we put more drivers? Would this algorithm work better if we are undersupplied, or will it be a problem if we're well supplied? And basically simulate all the metrics we're tracking, like the way we are available to passengers, the way passengers tend to convert because the car is close by, or because prices are high, stuff like this. And everything can be simulated, and it's a great way to answer questions. And when it's not enough to have simulation, then we use A/B testing directly on passengers, because for some questions you can't only rely on simulations, especially when it concerns real people, the way they would interact depending on parameters you change. So yeah, so these are the three steps that we use that are like I think really important of what we do at Lyft is look at historical data. If you can answer your problem really fast by looking at historical data and visualizing it correctly, then it's a good thing. If you can't, then you can all rely on simulations, and if you can't, then you go into A/B testing. So that's about it for my presentation. So if you have questions, if you ask a question, you get a mustache.